So this lecture on Chebyshev inequality and weak Laplace number. So we know what is Chebyshev inequality. So formally the Chebyshev inequality is this. So sometimes it's also called Markov inequality. The theorem is like that. So let Hx be a non-negative Borel measurable function. Borel measurable function of a random variable x. If this expectation, this is the expectation of Hx exists, then for every epsilon positive, the probability of Hx greater than epsilon, this is less than or equal to expectation of Hx by epsilon. Now proof for discrete and continuous the two different case. I'll prove for continuous case and the discrete case in the book. So what is expectation of Hx? This is for continuous, it is the integration of Hx fx dx. So fx is the PDF of minus infinity. Now you can just break into two parts, two integral part. So one in the a and another is the a complement part, the same integral. So what is a? The set a is just set of all such x such that hx is greater than epsilon. So you just break into two parts, greater than equal to epsilon and less than epsilon. So then what? Then you just drop one part, the complement part. You know all the integral must be, since hx is non-negative and fx is also non-negative. So this part is integration is always non-negative. So you can drop this one part. So this is just integration about the a hx fx. But what is hx here? Hx is just greater than epsilon here. So it is just over this set epsilon fx dx. But what is this? This is just epsilon bar came out, and this integration of this just the probability of hx greater than equal to epsilon. That part, that the set of all such x. If you integrate this the density function, you will get the probability. So what are the different corollary of this? The corollary of this important theorem is like that. So first corollary is let just consider hs as mod x whole to the power r and epsilon as at k to the power r. Say r is positive and k is also positive. Then using this Chebyshev inequality, you will get the probability of mod x greater than equal to k is less than equal to epsilon expectation of x to the power r by k to the power r. And this is also called Markov inequality. This is also called Markov inequality, and this is called Markov inequality. And if we put corollary 2, if we put hx equal to x minus mu is the expectation of x, and if you take x epsilon as a k square sigma square is the variance of x, then using that theorem we will get says probability of what we get. We get the probability of mod of x minus mu greater than equal to k sigma is less than equal to 1 by k square, and this is called Chebyshev inequality. This is called Chebyshev inequality. So we have to use this for weak Laplace number. What is weak Laplace number? The weak Laplace number is like that. So sometimes it's called the Quick law of large, WLLN, the quick law of large numbers. So let Xn be a sequence of random variables. The sequence of random variables. Now we write Sn as sum over all this I equal to 1 to n xi, or n equal to 1 to equal to n. Now the question is the important question is this: do there exist any sequence of constant, as a sequence of ak and bk, or an and bn? Bn is positive, it's like a variance, and n is the means. It's also called centering constant. A normal Bn is called normalizing constant. Bn is positive, and Bn tends to infinity as n tends to infinity, such that the sequence that Sn minus an, the centering thing, sometimes the expectation of Sn divided by that Bn, is converts in probability somewhere, or maybe 0 in probability as n tends to, is the question. Whether this can convert to the 0 in probability, in probability. Now the definition is this: may or may not happen that an and bn may or may not exist. We don't know whether an and bn are unique or not. So the definition is this: let this, okay, we have this thing, xn is the sequence of random variable, and Sn is the summation of what I equal to 1 to n xi. Now we say that sequence xn obeys or follows the weak law of large number, with respect to the sequence Bn, where Bn is positive and Bn increased to infinity as n tends to infinity. So it is with respect to Bn. If there exists a sequence of real constant, again this is an, may not be positive, such that Sn minus an by Bn, this goes to 0 in probability as n tends to. So if such thing happen, we call this xn obeys that weak law of large number, and this n is called centering coefficient, constant. N is called centering constant, and Bn is called norming or norming constant. Sometimes it's used n as expectation of Sn, and Bn is the standard deviation of Sn. So it may or may not happen. Now when it will happen, this is a definition. Now there is a theorem. The theorem is this, the most important theorem is this: let Xn is a sequence of pairwise uncorrelated. This is important, not any sequence. It is pairwise uncorrelated. May not be independent, pairwise uncorrelated. Random variables with expectation of xn is mu n and variance of xn is sigma n square. Maybe the different and may not be the IID, may not be the identical distribution. This is dot, dot, dot. So it's n, not I. So it's n equals to n equal to 1, 2, 3 dot. Now, if that sum over I equal to 1 to n sigma square goes to infinity, that summation goes to infinity as n tends to infinity. Sigma may not be goes to infinity, the summation goes to infinity. Then we can choose n like that. Then we can choose n the summation of this. So the expectation of xn. So summation of I equal to 1 to n mu I. And bn you can choose as the variance. That the variance is not a variance of xn because it may not. Okay, it's a pair is uncorrelated, so it is a variance, right? So variance of x1 plus x2 plus xn is just the variance of x1 plus variance of x2 dot variance of xn, and the twice the covariance of xi xj, the summation of I not equal to I less than j. So that part is 0. So that is the actually the variance. Variance of that the variance of I equal to 1 to n, variance of this. So then what thing then this follows the weak law of large number with this centering coefficient, centering constant a n as the expectation of xn as a summation xn, and this bn is a variance of the summation xn. So what is this? Then we have this that is the sum over I xi minus mu I equals to 1 to n divided by sum over sigma I square I equal to 1 to n goes to 0 in probability as n tends to infinity. So this is a theorem, and this is very easy. You can prove using just Chebyshev inequality. So what is by Chebyshev inequality? The proof is like that. So Chebyshev inequality says that the Sn minus the expectation of that Sn, which is I equal to 1 to n mu I greater than epsilon into sum over I equal to 1 to n sigma square. This must be less than or equal to the expectation of all this that numerator part, the expectation of summation xi minus mu I whole square, sum after taking the summation divided by summation then square. It's not a square and then summation then square divided by epsilon square into sum over sigma square I equal to 1 to n, and then again whole square. Epsilon square k square. So k is this summation I equal to 1 to n sigma square. Now what is this? This part is actually 1 by, this part is cancelled out. This is nothing but summation of this. This is uncorrelated. The expectation of summation of this what is summation? Since it's uncorrelated, we have this. We have the expectation of summation xi minus mu I, then whole square. This is nothing but summation I equal to 1 to n sigma square. The other product part is 0. So one part is cancelled out, the another part is epsilon square summation I equal to 1 to n sigma square. But we assume that this part is goes to infinity, so this goes to 0 as n tends to infinity. So that means this probability less than something which tends to 0. That means that this probability part tends to 0 as n tends to infinity. So this is that means this satisfies the weak Laplace number. Then what is the corollary? The corollary of this is this. There are several corollaries. Corollary 1 is if xn are just I, not IID, it is just R x's are identical distributed. Identical distributed. And may not be independent and pairwise uncorrelated. With that expectation of xi is mu I and variance of xi is sigma I, and sigma is which is finite. Both are finite. Oh, sorry, it is not sigma, it is just a same variance, sigma square. The sigma square. The expectation is different, but the variance is common variance. Then what happens? Then we can choose. Then what is A? A will be then n mu. Oh no, this also equal. This must be equal. Otherwise, it can be n mu. So the mean and the variance is same, but may not be the identical. This is identical distributed, may not be independent. Sorry, this is identical distributed. That means mean and variance is same, but may not be independent, may not be IID. So same common mean and common variance. In that case, what will be the AN? Then AN will be just n into mu. And what is Bn? Bn will be n into sigma square. And this goes to infinity as n tends to infinity. So we can choose this. So using that theorem, we have this. So summation I equal to 1 to n xi minus mu divided by n sigma square. This goes to 0 in probability as n tends to. So the condition automatically hold that sum is that part. So if it is pairwise uncorrelated and identical distribution, then weak Laplace number hold with centering constant n mu and norming constant n sigma square. Now, but we want something more than that. We want the denominator much lesser order. You know, in central limit theorem, this is actually this denominator is root n sigma. So we want to know whether this is if you divide by some larger thing, some n or n square or n cube, that must be goes to 0, no doubt. But if you divide by say root n, lower order, so whether this goes to 0 probability in 0 or if it not goes to 0, what is the distribution of that? Is that distribution it's a good distribution or not? So that is a question. So can we just reduce the degree of the denominator thing? Now the next corollary is this. Corollary 2 is this. If we choose say Bn equal to n, then n tends to infinity. Bn tends to infinity as n tends to infinity. Now, provided we can choose that, we can choose Bn like that, just n, not just n sigma square or n summation or sum over I equal to 1 to n sigma square. We can just choose n, Bn equal to n, if provided that summation sigma square equal to 1 to n divided by n square, that goes to 0 as n goes to. And if that goes to 0, if we choose Bn, then the condition for this weak Lovelock number holds. Now, can we choose any other thing? Yes, you can choose Bn like that. You can choose n as n mu in our corollary 1, and Bn is n. Since why we can choose that? Because n sigma square, that is the summation of sigma square, is n sigma square by n square, that goes to 0 as n tends to infinity. So we can choose that. Just we can choose not by just n sigma square, we can just choose a divide by n. In corollary, we can choose if we just this part, this denominator part, this denominator part is n sigma square, you can just n, because if we just multiply by a constant, then if some random variable x goes to 0 in probability, if you multiply by sigma square, this also goes to 0 in probability. So you just drop this sigma square part. So then corollary 1, what happened? From corollary 1, we get that part. If so, from corollary 1, we can have this corollary 1 to corollary 4. If xn as pairwise identically, pairwise uncorrelated, and identically distributed, random variables, with finite variance, obviously that sigma square must be with finite variance. Sigma square. Then Sn by n goes to mu. So in probability. So this is the weak Lovelock number. So we just take n, just not n sigma, so we can take this n here. So in corollary, we just take if we take just n square, n divided by n, so summation xi minus mu, and summation xi minus mu is just summation xi minus n mu. Now summation xi is just sn minus n mu by n, that is sn by n minus mu goes to 0 in probability. So that means sn minus sn by n goes to mu, goes to that mu, that means a common mean. So if it is identically distributed, xn is identically distributed and pairwise uncorrelated, may not be independent, then that sn by n, what is xn? It is a mean. It is xn bar, x1 plus x2 plus xn by n. That goes to the, so converts to that expectation. So x1 plus x2 plus xn by n goes to the expectation of xn. It is common expectation, especially x1 or expectation x2 in probability. So that is called the weak Lovelock number. It is actually the weak Lovelock number. So there's a we toss a coin. And this outcome of the probability head is 1 and the tail is 0. That means x1 repeatedly toss. So it is actually independent. So that means independent. That means it is uncorrelated. Now, if you take say for head is 1 and tail it is 0, and then the expectation of x is p. That means the probability of head is p. So you can easily use that thing to be. So example is that. So toss a coin repeatedly, and so x of head is say 1 and x of tail is 0, and probability of head is p. Then expectation of x is p. That is the mu. So now you coin repeatedly. So it is x1, x2, this xn. This is the sequence, and for every, so it is xi for all xi. So all this is mu. Mu is here p. Now what is the variance? Variance, actually no need of variance. We just Sn by n. So that means Sn by n means that is x1 plus x2 plus xn. This random variable divided by n goes to p in probability as n tends to. That means the number of heads. This x1 plus x2 x plus xn is just the number of heads. Remember, this is number of heads. Number of heads occur in n toss divided by n. So average number of head occurs. That is. So if they say we toss 1,000 times and there are say 600 many heads, that means 601 and 400 0. That means 600 by 1,000, and that part goes to the probability of head in probability. That is for the large n, you can just think that average value of average number of head occurs is very close to the probability of the head occur. So if you toss 1 lakh times, and if you get 40,000 many head, you can say the probability of head is just 0.4. Can you say just 0.4? No, it's not a 0.4. It actually goes to some number which may be very close to 0.4, and in probability. That means in probability means so taking 0.4 is high probability. Maybe it's 0. Can't be 0. Maybe it's a 0.1. Maybe it's a 0.99. But maybe it's a 0.01 probability of head. But that probability is very low. The most probable part is the 0.4. May not be 0.4, they're very close to 0.4. So around 0.4, the probability is high. The p, the p is the probability of head, and that is around 0.4. This probability is high. So p maybe lies between say 0.3 to 0.5. You can say p with high probability p is 0.3 to 0.5. So remember that p is actually p is not random variable, but still we can talk on that. High probability thing, like in confidence interval. In confidence interval, what do we say? We say x1, x2, xn is a sequence, and then say sample, and then mu is some parameter. Mu is some parameter. And in hypothesis testing also, we say the probability of say some function of xn less than or equal to mu, less than or equal to some other function of xn is this. It is not that the probability of that mu is not a random variable, but the interval where this random variable lies, that interval itself is random. So that's why the probability came. So interval is random. So say xn, the mu lies between say an and bn, or xn and yn, between these two random variables. This probability is something that we can see. So mu is not the random variable. The random part is the boundary is random. If you take the other sample, the boundary will be changed. The mu is the parameter. So this is actually the weak Laplace number, and there are several versions of this weak Laplace number, several things, but we know in our syllabus we just this is the in our syllabus this is all for weak Laplace number. There are other 3-4 versions of weak Laplace number. We complete our syllabus here up to weak Laplace number. In our syllabus, strong Laplace number also there, but we just we complete syllabus up to weak Laplace number. We omit the strong Laplace number in this year.